now applies to what I'm learning now. And on top of that, in this case, if you look at a cell phone, how was the battery now reconfigured so that it makes something a little bit thinner, so the cell phones that I carry around are not as chunky, right? Even now, you guys just heard about the new Apple Pro iPad that came out. It's only 5 millimeters, actually 5.1 millimeters thick. So how is it that they've been able to convert a battery that's chunky like this into something that is only 5 millimeters thick and is able to power your iPad for a significantly long time? So what's all going on? So this part now is our sort of work on figuring out how we make these reduction and oxidation reactions useful for us. Because at the end of the day, all of this is like, how do I benefit from it, right? How do I make use of it, right? So somebody walking around with a pacemaker is alive because of a battery. So in this case, what is going on? So the very first thing that we take a look at, and we're going to be breaking down a few of these things, and then I'm going to be getting you guys to write a lot of gibberish down that you guys will not understand, but we'll break it down eventually. So first thing is, it says electrochemical cells use energy released by a spontaneous redox reaction. So if we were to take a look at this spontaneous redox reaction and we go into our data booklet, what this means is what we have learned before is that it is going downhill. So we are now deliberately putting two reactions together such that they're going to have a downhill relationship. So you're going to be producing electricity. So specifically, we are looking at a strong oxidizing agent and a strong reducing agent. Okay, so that's the first part. So going back over here, taking a look at this, and we're forcing electrons through an external pathway. So we're going to be a little bit more clear in a few moments. Now what we want to do is we want to take a look at some of the technical things of how we determine this. So first of all, voltages are obtained from page 8. So the very next thing that I want you guys to see in your data booklet is so far we've just looked at the chemical reactions that are taking place, and we're looking at, let's say, a downhill reaction, but now what we're doing is we're going to now start looking at these voltages down along the right-hand side. When you take a look at this, it says here, all potentials are measured at standard state conditions, which means that it is 25 degrees, 1 molar, and 1 atmosphere. So if you look over here at your data booklet, all of these numbers here that you see right on the side are measured under a very specific condition, which is that the ion concentration is 1 molar and the temperature is 25 degrees and it is at 1 atmosphere, hence sea level. Now Raya's going, well, why does that matter? It does matter. She's got a scrunchy face. She's thinking. And now, and so does Ashley. Okay? So in this case, I want you to think about the following. How many of you guys have, seen in movies, or this might happen to you guys, is that, you guys have like a regular combustion car. You get into the car in the wintertime, it's going, it doesn't turn over very easily. Whereas in the summer, boom, right? It just starts automatically, no problem. And we're not talking about the little button that you push. It's like with the key, it goes, vroom, right? And so in this case, or even now with the Tesla, they were saying, oh, Tesla, we have like a 500-kilometer range per charge, but people living in Ontario goes, you lie. I can no longer use that little degree sign. It just becomes an E with no degree sign on it. So therefore, the degree sign here is very significant in the sense that it specifies a very specific condition under which you generated these values. Now, number 3 over here, if you were to take a look, They are all relative based on the hydrogen half cell. So what do we mean by that? So if again I go down to the data booklet and I look at all of these numbers here are not absolute. So do you see right now if I go down, the numbers are getting smaller and smaller and smaller. Do you guys see that? And then until I reach right over here, aha, hydrogen. Do you see hydrogen right here? Do you see it's a 0? It's not a 0. Right? It is the reference by which we compare everything else. Okay? So for example, if I made myself as a reference for age, all of you guys compared to me would be younger. Right? However, if I change the reference and I have a newborn child as your reference, what does that make you guys? You're all older. If I compare my age to somebody who is 90 years old, I'm younger. So at this point in time, we set this hydrogen as our standard, as the basis by which everything gets compared. So in this case over here, if I go up to this copper right over here, this is saying compared to hydrogen, it's a plus 0.34. We'll talk about what it means later on. However, if I was to go ahead, and I'm going to use purple, and say this is now going to be my new standard of comparison, and I set that up as 0 volts, would copper here stay 0.34? No, this would no longer be 0.34, this would now be 0.20, isn't it? Because my reference has changed. Does that make sense? So I had just gone through over here 3 statements. First one, voltages are obtained from the data booklet. Number 2 is that the potentials are under standard state. And number 3, they are comparisons. Do you need to write a few things to yourselves before we move on? A little bit different, okay? Right now, I'm just going to deal with this one. We will deal with that second one at a later date, okay? Now, the first thing that I want you guys to make a note of, and that you guys want to sort of begin to recognize, is that this is a battery. Recognize that this is a battery. So in this case over here, you're also going to be required to determine which metal is oxidized. So come down here. And which is reduced. So I'm going to pause here. So again, do you see 2 words? We have oxidation and reduction, yes? So first of all, I want you to see that on this side, we have the hydrogen. Do you guys see that? Remember, we had just said this is our reference. And then I have some other metal over here, and this is zinc. Now, before we actually take a look at this, I want you to take a look at how the 2 equations are written. Take a look at the hydrogen. Take a look at the electrons. For the zinc, take a look at the equation. Take a look at where the electrons are. What is happening on the hydrogen side? So notice it's a single arrow, yes? The electrons are on the reactant side. That means you're adding electrons. That means you're gaining electrons. That means it is being reduced. So this is your reduction half reaction. So now if you take a look at the other one, where do you see the electrons? They are on the product side, so you're now giving away electrons. You're now losing electrons. So this side is the oxidation half reaction. Okay? Now, here's the deal. Up until this point in time, all your reactions, you stuck a metal into a solution and a reaction happened, right? And then we balanced the two half reactions and we said, here's a reduction, here's an oxidation, and boom, they're reacting. Now, at this point, do you see how the reduction half reaction happened in this beaker on the left? And the oxidation happened in this beaker on the right. Do you see that? So in this case over here, they are deliberately kept separate because you know that this is giving away electrons, yes? But if they're in the same container, they will just directly give each other electrons. But in this case, they are forcing the electrons through a wire. So do you see this wire that's coming through? And it's connecting from one side to the other. And based on what you had just said, this is oxidizing, meaning that it's producing electrons. That means it's shoving electrons out of this side and pushing it to this side in the other beaker. Yes? And then what's happening in this side is the electrons are coming in and they are now being absorbed by the H+, aren't they? Here's the question. The electrons are being pushed through a wire. So the electrons are flowing through a wire. What do you call electrons when they're flowing through a wire? Electricity. So this is now where your electricity is coming from. One side is oxidizing and the other side is reducing. Okay? So this battery that I have in here, as it's functioning, one end of it is oxidizing and one end of it is reducing. Now, when you take a look here, there is also this little guy. So I'm now going to start getting you guys to begin to write things that don't make sense. This is called a salt bridge. So it allows ions to flow. It maintains charge neutrality. So the circuit can be completed. It can be made of any ionic solution. The positive ion, which is the cation, goes to the cathode. And the negative ion is the anion, and it goes to the anode. And the last thing I want you to write on this is your hydrogen fuel cell or hydrogen cell. So this here is your reference electrode, because this is your hydrogen. Now all of this will make a lot more sense in a few moments. Okay, now let's fill in a few more blanks and you will continue to be confused. Okay, so the cell voltage is calculated by the following equation. E naught cell is equal to E naught oxidation plus E naught reduction. So it says over here, if you reverse the direction of the equilibrium, you switch the signs of the voltage. You never ever change the absolute value of the E naught value from the table. Okay? Positive voltages are spontaneous. Negative voltages are not spontaneous. We will deal with the cell notation a little bit later on. We're not going to cover that right now. But the final thing is, anode is oxidation. Cathode is reduction. Anions move to the anode. Cations move to the cathode. Now, to help you remember some of this, to remember this particular concept, you can go and aux cared. Why do we care about cows? Because this is anode is oxidation, cathode is reduction. Therefore, a cow is relevant here. Sean goes, this is so weird. Yeah? Yeah. Okay? Or another way that you look at this is vowel goes with vowel, consonant goes with consonant. And in general, anode and cathode is referred to as an electrode. So new terminology here. Okay? So, let's take a look at the next page. So what we're going to do is we're going to try to do our analysis and we're going to try to answer these 10 questions. So before we do that, we have to construct this diagram. So over here on the left, I want you to put CO here. And then down at the bottom, I want you to put down 1 molar COCl2. Or another way that we write this is 1 molar CO2 plus. On the other side, this is the zinc. And this is going to be 1.0 molar ZnCl2. And then we have 1.0 molar Zn2 plus. Now, I want you to notice at this point that this and this are viewed as the same. What does that imply about my Cl? It's a spectator ion, okay? So in this case, all that I care about is the partnership of CO and CO2 plus and zinc and the zinc 2 plus. Do you guys see that? Okay? Now, when you are starting this, you're going to be answering these 10 questions. So the first one says, identify the process occurring at each electrode. So the first thing I'm going to do is I'm going to take a look. It's going to be between CO and CO2 plus, and also between Zn and Zn2 plus. Those are my potentially reactive species. Now what I do is I take a look at my data booklet. And what I'm now going to look for, so I'm just going to erase this out, is I'm going to look for those two substances. So do you see over here, I have my CO and CO2 plus right here. And then, if I take a look, do you see my zinc 2 plus and zinc? Now remember, this is a battery. So if it's a battery, what two substances are going to now react together? So remember, it's a battery, it's a spontaneous reaction. I have these 4 species available to interact, and if it's spontaneous,
CO2 plus and zinc.
right, because I have CO2 plus and I have zinc because I want a downhill reaction, don't I? Okay, so what I'm going to do right now is I'm going to rewrite this on my page just so that I can then refer to it as I do my analysis. So for question number 1, it is going to be CO2 plus 2 electrons giving me CO, and my E naught over here is going to be negative 0.28 volts. I'm going to go down further, and you saw this positionally. Zinc 2 plus 2 electrons gives me zinc, and my E naught over here is negative 0.76 volts. And we had just concluded that it is going to be the CO2 plus and the zinc that are going to want to engage in a reduction and oxidation reaction. Okay. Now, when we take a look here, seeing that I circled these two now want to be reagents, don't they? So if cobalt is on the left-hand side, it's going to react, and it's going to want to go in the forward direction, isn't it? The zinc is on the product side right now, but it wants to react, so what direction is it going to go? It's going to go in this direction, isn't it? Now I want you to look closely. When you take a look at the forward direction, the electrons are on which side? The reactant side or the product side? It's on the reactant side, so it's absorbing electrons, yes? And it's gaining electrons, yes? So if it's gaining electrons, what is that forward direction called? It's the reduction reaction. Yes? Now, if I take a look at the zinc wants to go in the opposite direction. Yes? So the electrons relative to the zinc is on what side of the reaction? the zinc is on the right-hand side, the electrons are on the left-hand side. So it's on the opposite side of the arrow, yes? So if it's on the opposite side of the arrow, then it is on the what side? Reactant side or the product side? It's on the product side. So if it's going backwards, it's giving away electrons. If it's giving away electrons, what process is that? Oxidation. So do you see now you have a reduction half reaction and you have an oxidation half reaction happening? Yes? Okay. So in this case over here, it says identify the process occurring at each electrode. So on this side over here, this is taking place, reduction. So therefore, right now, I'm going to write down reduction is happening right here. What is happening on the zinc side? Oxidation. Good? Okay. Now it says, label the anode and the cathode. So if I know that the left side here, reduction is taking place at the electrode, and on the right-hand side here, oxidation is taking place at the electrode, what do I call this electrode? Where reduction is happening. And ox paired. It's the cathode. So this is your cathode. On the opposite side, you have oxidation happening. So what do we call that electrode? It's the anode. So far, so good? I'm going very slow. Edwin? You look dazed. Okay. Now, I'm going to skip through 3 for the time being. And it says here, calculate the cell voltage. So what voltage is the cell going to generate? So here is how I would then calculate the cell. So this would be number 4. So in this case, you notice that the cobalt 2 plus is going in the forward direction, yes? So at this point in time, I write it as is. And my E naught over here is negative 0.28. Okay, let me just write this a little bit smaller. So CO2 plus 2 electrons in equilibrium with CO, E naught is equal to negative 0.28 volts. Now, we take a look at this one. Based on how it was written in our data booklet, the reaction is written in a reduction form, but we want it to be oxidized, don't we? So therefore, what do I need to do with the reaction as I go in the forward direction? I need to flip it. So in this case over here, I take the zinc. I'm now going to flip it. So this becomes Zn in equilibrium with Zn2 plus 2 electrons. Now, something important happens here. Do you remember in the last page, it says, if you reverse the direction of the equilibrium, you switch the signs of the voltage. So over here, notice I have flipped this equation. The original equation was written in the reduction way, but I flipped it over. So what should I now do to this value here? I make it positive. So therefore, I keep the E naught value the same, 0.76 volts, but this time now I just change it into a positive value. Okay? Now, before we go any further, notice that this first reaction is the reduction reaction. The second one here is the oxidation half reaction. So therefore, I'm going to put a subscript here. This top one here is for the reduction. And the second one here is the value for the oxidation. Do you guys see that? Now I can add up my equation. So do you guys see how the two electrons cross out? Do you guys see that? So now if I write this, this will be CO2 plus Zn in equilibrium with CO plus Zn2 plus. And now if I take a look at my E naught, what does that become? So going back to the previous page, to figure out the overall voltage of the cell, what do I need to do? I add the voltage of the oxidation to the voltage of the reduction. So in this case over here, I take my values and I'm going to have negative 0.28 and I add it to 0.76, and my voltage here for the entire cell is positive 0.48 volts. So if I put a voltmeter here, this would read 0.48 volts and it would be positive. So do you see how I've combined the reduction half reaction and the oxidation half reaction, just like how you guys did before? Do you guys see that? But this time now, one of these reactions is happening in one beaker, the other reaction is happening in the other beaker. We just forced it apart. Why? Because then we can see the electrons go through. Okay, that's number 4. So what I would like you guys to do right now is, can you guys do questions numbers 1, 2, and 4 for this reaction down here? Good luck.